record. Excellent. Okay, so as we finished up with last week, we were talking about indexing in R and Python, as you'll remember, and we spoke about how R is 1 indexed and Python is 0 indexed, and that's where we left it at the end of last week. One of the other major differences that exists between R and Python is basically the way in which the programs and the code is designed to be written, or rather is like intended to be written by the people who use it most. And that is to say that R is very much what's called a functional language, a functional coding language, and Python tends to be very much what's called object-oriented. And so we're going to see what that means here quite briefly. So as an example of how to demonstrate the difference between object orientation and functional code, I've taken an example that's present in the literature, that's rather we use quite a lot in our literature and in our classes, which is, for example, just doing some simple matrix multiplication, or rather an eigenvector eigenvalue decomposition of a couple of matrices. And so what you can see here is I've just created a matrix. My matrix has this shape. It's a 2x2 matrix with values 6, 2, 2, 3 in that orientation. And I've made the same matrix over here with Python using my NP array and my reshape to size 2, 2. And then what we do in R, if we want to calculate the eigenvalues and eigenvectors of this matrix, is we just use this function eigen, and we enact that function on the matrix. And that gives us the eigenvectors. Now, as you'll all remember from your undergraduate mathematics, the results of the eigenvector and eigenvalue decomposition mean that we can reconstruct the original matrix A by using this matrix multiplication of the eigenvector matrix, the diagonals of the eigenvalue matrix, and the transpose or the inverse of the eigenvector matrix again. And so if we do that, and the way in which we're going to do that in R is using this special function here, or this operator, which is actually just the matrix multiplication, inner dot product multiplication symbol. And we're just going to do exactly that formula. We're going to take the eigenvectors, we're going to multiply them with the diagonal of the eigenvalues, and we're going to multiply that again with the transposition of the eigenvectors. And we get out what we put in. So that's just to show you an example of using using our functions, or rather operators, to do something like this example. If we were to do the exact same thing in Python, what you see is you have very much the same sort of thing. You have your matrix creation. We then have this numpy dot linear algebra dot eig function. And so we're using a function that is embedded within the linear algebra part of NumPy. And again, it acts upon matrix, and we see we've got this funny tuple unpacking thing that we discussed last week, where this thing really produces a list, which one entry contains the eigenvalues and one entry contains the eigenvectors, and we've unpacked it into those two variables, one called eigenvalues, one called eigenvectors. And we then do this same piece of mathematics here. Now, you'll notice that the way in which we're doing it is slightly different. And that is to say that we've called the dot product. So we have the eigenvectors here, right? This is the first thing. And then on the eigenvectors object, we apply a dot product with the diagonal of the eigenvalues. So this chunk here is the object-oriented way of doing that first chunk there. And that gives us a result. And that result, we then want to enact another dot product on. So we take the result, take the result, and we do another dot product, but now with the transpose of the eigenvectors. And so this is an example of where the object orientation is actually a little bit difficult to read. It kind of makes things a little bit more complicated, I would say, to read than this operator format. But to be totally fair, this operator format is actually kind of cheating, because formally, if you wanted to be functional, if you wanted to write this in the functional code sense, then the way in which you would do it is using something that looks more like what we've got here. And that to people who aren't familiar with R, probably looks like complete gibberish. But it's essentially saying I have a function, which is this operator, this dot product operator, and I want to use a dot product of this thing with this thing. So that's the first step. And then I take the result of that dot product, and I want to do another dot product with the result and the transpose of the vectors. So that's, again, it's sort of more complicated again. But that is the fully functional way in which you would write something like this. And it's basically just the whole point of the difference between object-oriented and functional programming is whether or not you have a function that acts on things that reside within the function call, so within the break, the parentheses, or you have an object and that object has functions attached to it, and you used those attached functions essentially to do whatever you want to do. That's kind of the difference. So you can think of it as the name suggests, the functional code uses functions as the highest level object, and then functions wrap objects. And in the object-oriented code, you have objects as the highest object, as the highest thing, and they contain functions that you can use. It's worth saying that this really easy to read syntax was actually also implemented in Python 3. So you don't actually have to do it like this for this particular application. They have this new thing, a functional operator, which is the @ symbol, which does matrix multiplication, if you're interested in doing matrix multiplication. And you end up with the same result in R and Python. We can then extend this to a different application, which is probably not super important, other than to just say that there are another case where instead of having the purely symmetric matrix, which we assumed here, if you don't have a purely symmetric matrix, then the mathematics changes a very little bit, but you have the same result. Okay, the main motivation for object-oriented programming is the way in which you can create objects that have like a class of objects that have functions attached to them. And so the way in which I'm going to demonstrate the use of object-oriented programming quite quickly is we're going to together create a fake class, or a useful class that we might want to use for our work. Now, the class that I'm going to create is called human, and I'm going to use the human class to create an entirely fictitious person. Okay, that entirely fictitious person is named Angus. They have the occupation lecturer. They are 165 centimeters tall, and they are 31 years of age. So again, totally fictitious, bears no relation to reality. With this class object thing that we've just created, what we can do is we can create in Python a person, and that person is of type human, and they inherit all of these things that we just created with this class statement. And so if I print person1 and then I want to access the name of person1, then I get out the name of this person, Angus. If we have, yeah,
question,
Marcel, yeah.
Now each human would have the name Angus. Am I right?
Exactly.
Okay. Good.
We'll get to the generalization in just a second. Yeah. So we've got this object which has the person, and the person always inherits, as Marcel just said, always inherits the name Angus. They always inherit the occupation lecturer, etc., etc. And if we just print person1, then we get this really cryptic looking thing. So that's not super useful for us, right? But it's a demonstration of how we can create a class, and that class can have different variables attached to it that automatically get assigned to an object when we do this assignment here. Let's now do something which is a little bit more useful and create a class human that doesn't have the properties of Angus hard-coded into it. And instead, what we have is our class human. And when we initialize the class, we want to initialize that class with a person's name, occupation, height, weight, and age. Okay. And additionally, we're going to define this thing, which is just called str. And what this does is it dictates what happens when I type print person. The details of that, not super important for us right now, but just so you know. So again, now what we do is we create person one, and our person one is a human, but now we actually assign the details that we want. Okay, so we assign Angus, he's a lecturer, he's 165 centimeters tall, he weighs 65 kilos, and he's 30 years of age. And now if we do print name, again, person name, we get name out. But now if we do print person, we get this more interesting or more useful output. That is to say that this is we have printed a person named Angus, who's 30 years old, 165 centimeters, and weighs 65 kilograms. The main utility of classes and of object orientation is the combination of classes and functions that act upon those classes. So, what's an obvious function that we might want to allow a human object to have? Well, I would argue that the first thing that a human object ought to be able to do is to grow, right? Fairly simple. So what we're going to do is we're going to define a function that's called grow1. And what that function does is it increases the age of the human. It increases the weight of the human, and it decreases the height of the human. I think all fairly accurate statements of what happens when somebody whose name is Angus, aged 30, increases in age. We've also made a grow n function, which does the same thing, but instead of doing a unit in year, it acts n years at a time. So again, we create our person, Angus, lecturer, 365 centimeters, 65 kilograms, and 30 years of age. And we print that and we get the same output out. We now take our person and we activate the grow1 function. And what happens is our person grows a year older, they decrease by 0.5 centimeter in height, and they gain a kilogram. If we now chain together a bunch of functions, so we say, I want this person to grow 10 years, I want them to then grow an additional year and grow an additional year again, then all of a sudden we end up with a person, Angus, who's 43 years old, is 158 centimeters tall, and weighs 78 kilograms. It's not exactly boding well for the future of this particular hypothetical person who is totally hypothetical. One important thing to note about the way in which these classes inherit and these functions act is that they act in place. So this here, this chain of commands, doesn't just happen within this print statement. It happens on the object human Angus itself. And what that means is that if I print person now, after doing all of these steps, I get back the last state of the object that I have looked at. So these things are actually inherent attributes that you are modifying when you call each of these functions. Okay, it's an important thing to note. So that's basically the main utility of object orientation. That's why we do it. That's why you tend to see it being so popular, is because of the way in which you can construct a class of object, and you can then assign attributes to that class and functions that act upon that class. And then you can do all sorts of really useful, crazy chain together things with that class. That was all done in Python. The bottom section of this slide is just to say that you can do exactly the same thing in R should you want. There are actually 4 different ways to implement object orientation in R. I'm not going to go through why they're different, other than to say that the last one, R6, is the thing that looks most like what we just saw with Python. And so I'm going to use R6 and I'm going to do exactly the same process. I'm going to create a class called human that has name, occupation, height, weight, and age. When that class is first called, you need to initialize it, and it needs to be initialized with these properties. It's got a print function that prints something that's sensible. It's got a grow1 function that does the same thing we saw above, and it's got a grow_n function. And then we can play exactly the same game that we just did in Python. We can create person1, who's a human that we've newly generated. It's a different syntax there, but with the same properties. and then we play the same game. We have person 1, we grow them by 10 years, then by another year, then by another year, and we end up with the same output. Okay, so that is just to say that that's all the same sort of syntax. But in practice, generally, we don't use object orientation in R just because it's not as popular. But it is gaining in popularity, I must admit. The next thing, the last two things that we're going to look at very quickly in this R Python crash course is two things that basically everyone is going to need to do at some point, which is read and write data and do some plotting. I won't go in a great deal of detail through this. If people are interested in how to read and write data and how to make the plots that I'm showing, then this should be a little bit of a guide. But so what I've done here is I've just created some fake data, which is a combination of integers, float values, real numbers, and strings and characters, random characters. And I've then written that data to file using this. You'll recall we spoke about this thing, data table, which is a very, very rapid way of reading, writing, and analyzing data in R. So I've used the file write function within data table to just write a fake data.csv. And then I've now read in the data again using the default read for ASCII data in R is called read.csv. And I just said, how long does it take to read this catalog in? And it took, here we go, four and a bit seconds. If I read in the exact same data, instead using the data table fread, it's the equivalent of file write, it's file read, then it reads in that catalog in 0.3 of a second. So you can see that there is more than a factor of 10 improvement in the speed with which you can read large data using this data table. And just for comparison, I've then done exactly the same data read using NumPy, using this function from NumPy gen from text, which is the standard way to read ASCII data in NumPy, and also using the pandas equivalent of this read.csv, which is read_csv, and then I've timed them both. So these two functions basically just start a timer, do the read, and then stop the timer and tell me what the difference was. And what you can see is that when you read that data in with NumPy, it takes sort of 2 seconds, so better than the default read in R, but not as quick as the data table. And pandas is faster than NumPy again, and gets to within a factor of 2 of the data table implementation. So this is just a demonstration, sort of a lookup of how you read data at different speeds in the two languages. There's also a plethora of different types of data that you can read and write. So you can read and write fits data, which is very common in the natural sciences. It's a binary format of data. But then there's also all of these special types of data that is designed for very, very rapid access. So Pickle is an example that Python people will know. The R data system is a format that's used quite a lot in R. It's basically an R equivalent of Pickle. And then there are things which are unique or outside both the languages, one of which is called Feather, and this thing is blazingly fast because of the way in which it's made, but it is quite restrictive. And I'm not going to go into the details of how you do this. If people are interested in having examples of how read and write fits or read and write binary files, then I'm happy to write those. So please just let me know in the questions. The last thing I'm going to show is just an example of how you do plots. In Python, in R, the plotting functions are available both within the base language and also with additional packages. In Python, plotting is basically contained to within the matplotlib suite of packages. So you can see here's an example of how I did the plots that we already saw last week in the modern science and the requirement of programming section. So this was the R code that I used to create this plot here, which essentially is just saying plot is the default scatter plot in R, and I want to plot X and Y data. And then these are all just additional sort of options. So I want to have a Y label, I want to have an X label, I want my color to be blue, and I want the title to be the properties of the best fit, is essentially what this is doing. If you then want to add lines to a function in R, you use the lines function. It's fairly straightforward. Again, just with X and Y and a choice of color and the line width and the line style. And this is, again, just using lines to do the dotted lines on the outside. And then lastly, if I want to add a legend, I use the legend command. So this is all just base R. It's, very, very simple sort of stuff. I'll leave that for people to have a look at, have a play with if they're interested. You can improve upon the base R plots by having additional packages. And the one which I'm going to use quite a lot is called Magic Axis. And Magic Axis is basically just designed to update how the axes are plotted, to make them a little bit nicer and more sort of normal in inverted commas for what we would use in science. So basically, if I use exactly the same commands and all I do is I change plot to mag plot, then you end up with this here, which is basically just a slightly nicer format for the plotting of the axes. And again, here's also the plotting in matplotlib. Now, in Python, in matplotlib, so we import from matplotlib pyplot, and this is a pretty standard thing to import as PLT, for plot, because then all of the different functions that we might want to plot are contained within this thing here. So if we want to do the scatter plot, we just do plot scatter of the X and Y data, and it's useful to assign a label to it. And that's because it's going to become important when we want to make a legend. If we want to then overplot the lines, so we just do plot instead of lines in R, it's just plot for a standard linear plot in Python. And then we can also overplot the uncertainties. We can add the title. And then the last step that we have here is to plot the legend. Now you'll notice that when we plot the legend here, we don't actually specify any commands or any additional options. We just specify plot legend. And that's because all of this information about the type of the lines that are used, the color that they're used, and the plot style, etc., and the labels, that's all encoded in these commands that we gave here. So that's where label comes in. Label comes in here, best fit model. You make this a bit bigger. Oops, I've accidentally highlighted everything. So we have, oops, scrolling too far. So we have the label here of this, et cetera, et cetera. So that's slightly more elegant in Python than it is in R, but otherwise they're basically equivalent. The last thing I'm going to show here is that there are lots and lots of different ways and different examples of plots that you can make in both languages. But this is really where the example function we looked at last week really comes into its own. So if I take an example, the Magic Axis has a function mag project, mag proj, and that essentially has the code required to create on-sky projections of data. And for example, if I just do example magproj, then there is a whole bunch of examples that it puts out. And this is an example of just a full sky plot where you can see the galactic plane is in gray. So that's the Milky Way galaxy in gray and where it sits on the sky. The yellow here is the plane of our solar system. The sun here is the sun on my birthday, because why not? And then we've overplot a whole bunch of locations of various data, for example, something that you might be interested in doing. You can also look at, for example, to making images. Again, just using the example code, I want to make look at the images that can be made with this mag image function. And again, we get a bunch of examples of different pictures of galaxies. So here we've got a bunch of single color, single band images. There's examples with annotations, without annotations. Then there's examples of galaxies shown in color with different bands and things like this. So these are all things that the examples just show you by default, and you can have a look at if you're interested in your own time, and changing settings to get slightly different looking figures and da-da-da-da. Okay, so that's the end of the lecture 1 from last week. We're now going to go on to lecture 2, but if anyone has any questions about lecture 1, then now would be a great time that weren't asked at the end of last week. Great. Okay, so I'm just loading in the new lecture. which will just take a second. Here we go. So now the section that we're going to be talking about this week is section 1A, and I've called it data description and summarization. And so just as an introduction, so now we're going to be looking at, so this is the start of sort of section 1. So you'll remember from the beginning of last week, we had sort of 4 sections that we're going through in this course. And this is the beginning of section 1, where we're basically going to be talking about how you describe data. This is going to be split into 2 parts, and the 2 parts I've sort of split into a discussion just about the notation that we're going to be using in this course, the types of data that we can have in a statistical sense, different types of frequency measures and how we make graphs of data and things like that. And then we're going to discuss what's called measures of central tendency and dispersion. So now, hopefully, a lot of this is stuff that you will have been familiar with through mathematics over the course of your careers to date. But if not, then don't worry, because this is obviously all things that we're going to be going through in some detail today. Next week, we're going to be looking at different graphical comparisons between different data distributions. We're going to be looking at how you can compare different point estimates and dispersion statistics that we're going to talk about up here. And we're going to look at a few other things, correlation and covariance and practical data mining. But so these are the things that we're going to cover today. Again, if you have questions, feel free to add them on the Slido as we go. And if you like a question that somebody asks, then obviously feel free to upload it. Okay, so the first thing that I think is important for us to discuss about before we dive into the statistics portion of the statistics lecture series is just a rough demonstration of the notation that you're going to be seeing a lot of, and the names that we're going to be giving to a lot of different things. So one of the things that we're going to be hearing a lot of, as you might expect, is the concept of an observation. And so an observation is given the symbol lowercase omega here, and is essentially any individual measurement that we're making is going to be called an observation. Okay, a collection of observations is what we call a sample, and a sample can have any extent. And here, so you can see we've got n observations omega, which have the indices 1, 2, 3, all the way through to n. And so a sample is essentially any collection, any set of individual measurements. Yeah. The number of observations within a sample is given by this absolute value of omega, which is known as the cardinality in set notation, but you can basically just think of it as the length of the number of observations that we have. And so you'll be seeing n cropping up quite a lot, but occasionally you'll see this cardinality symbol as well, just for the FYI. And the last important definition to have in this sort of set of definitions is the concept of a population. And a population, given the symbol capital omega, is the collection of all measurements. Okay, and we're going to sort of point out how they distinguish from one another in a second. Okay, so every observation omega generally has tagged to it at least one or more variables. Now, it has to have one variable, right? Otherwise, there was no observation, somewhat by definition. And we usually give variables the symbols of Roman letters. So these are X, Y, Z, A, J, K. But sometimes we tend to give them the value X with a subscript, and that's usually if we have lots and lots and lots of variables. So if we have more than can be reasonably shown with different letters, then we'll just show them as X1, X2, all the way through to XP, of however many variables there are P. The observations of each variable are given the lowercase equivalent of their letter. Okay, so if we observe n observations of a variable y, then those observations form the sample y1, y2, y3, all the way through to yn. Okay, hopefully that's clear. If a variable follows a particular probabilistic distribution, then we'll assign that with a symbol tilde. You don't necessarily need to understand what that means at the moment. I've included that here mostly for posterity, for when you look back on these lecture notes once we get to the probability section of the course. But just FYI, that's why that's there. Now, you might obviously ask, why do we need to double up here with the omegas and the y1s, x1s, x2s, z2s, etc., And basically, the reason is because when we're dealing with data sets, we typically have observations, omega, which are tagged by multiple variables, right? So we might have the first observation, which has a particular value in X, a particular value in Y, and a particular value in Z. So you can basically think of the observations omega as the rows of this table and the variables as being the columns in these tables, and the values of the sets of each one of those variables as being the entries of these tables, right? So this is sort of the way to visualize what all this names and stuff means. Okay, so if we then want to ask the question, why do we make a distinction between a sample of objects and a population of objects, which is the whole sample, right? And essentially the reason that we do that is because generally in natural sciences, we never have a population of objects. That is to say that generally we have never made every possible measurement that can be made. Okay, so if we have a particle accelerator and we're looking at the particles that come out of a particular interaction, every interaction might be a single observation of the distribution, the population of all possible interactions. Now, obviously, to make measurements of all possible interactions would take forever, and therefore we never have a complete population. What we have is a sample that we then try to use to infer the properties of the population. Okay, and that's the main important difference that we have between the sample and the population. Okay, so we're never presented with all measurements in the most literal sense. Instead, what we have is a subset of possible measurements that we then try use to infer the properties of the population that we're interested in. Okay, there's another important distinction that we're going to see come up quite a bit later on in the course, but I'll flag here just for your reference. And that is to say that because of this distinction between the population properties and the sample, we also have a distinction between values that we estimate from a sample and the true values of the population. So if, for example, we have a true population, which is a Gaussian that has a mean and a standard deviation, then usually we would symbolize the population properties using Greek symbols. Okay, so the population mean is given the symbol mu, and the population standard deviation is given the symbol sigma. Whereas if we have a sample of observations and we then measure the mean of those observations, that mean is given a Roman symbol, is given the symbol, for example, X bar to mean the average of X, or S to mean the estimate of sigma, but not sigma, right? Because it's a sample estimate of the population parameter that we're trying to measure. And that sort of leads to another distinction that we make, which is between the value that we measure on a sample, or rather the value that is present in the true population, and an estimate of that parameter. And so if we have, for example, a true parameter, which we're just calling theta here, then the estimator for that particular parameter we delineate by having a hat over the top of it. Now, that sentence there probably means exactly nothing to the vast majority of you, and that's totally fine. I'm not expecting you to understand what that means just yet. It's something that we'll talk about quite a bit later on. But let's put all of that together into a really simple example with plain English to try and give you an idea of how all of this stuff mixes together. So we have a sample omega of n observations for a single variable x. And we know that that single variable x follows a Gaussian distribution, and the Gaussian distribution has true values mean, mu, and standard deviation, sigma. Putting that into math notation, we have observations that are drawn from a population where the number of observations is n. The values of x of these observations are drawn from the probabilistic distribution of a normal, of a Gaussian, which has mean mu and standard deviation sigma. The values that x takes for each observation is the set of values x1, x2, x3, x4, all the way through to xn. So this is just the column of our table here. Now, one other way to write that may or may not be useful is using a different notation that is commonly used in statistics, which is called mapping notation. And this here means exactly the same as the bottom thing. It's just another way of writing it. But it essentially says when you map the variable x onto the observations omega, you get the values x1, x2, x3, all the way through to xn. So we have this sample omega of observations of x, and we then say, for our science, what we want to do is we want to estimate the value of the population mean mu. So we define ourselves an estimate of mu, and we define that estimate to simply be the mean of the observations. So we define an estimator of mu to be just the arithmetic mean of the observations, x bar. We compute x bar and we publish our results. Okay, so that's essentially the whole process, going from data set through to science. Okay, and that hopefully should give you an idea of the sort of notation that we're going to use throughout the course. Now, don't get too hung up if this is all sort of, looks like it's written in Cyrillic. Then hopefully it'll become a bit clearer as you become more familiar with it over the course of the lecture. Okay, so that's the nomenclature and the notation thing done. So now what we're going to do is we're going to go through the fundamentals, as I like to think of them, as of data description. How when given a data set, do I fundamentally describe what is contained within that data set? Okay, so a lot of this should hopefully be very familiar to you all, because we're starting very much at the very, very beginning here. So the first thing that you want to look at, the one that you want to talk about when you have a data set, is the distinction between qualitative and quantitative data. So qualitative data are, very broadly speaking, just those data where you can't make a sensible ranking of different sets, of different groups of data. Whereas quantitative data are those where you can make a sensible ranking in a natural sort of manner. So here's, as a simple example, if we take a class, say a lecture hall, and we ask everyone in the lecture hall, what is your name? And then we rank the 6 most common names. Okay, so we see that we got 8 entries for Melissa, we got 9 entries for Bridget, we got 8 entries for Claire, we got 7 entries for George, 3 for Frank, and 5 for Harry. Okay, these are just the names that we were given by the students and the number of times which those names occurred. These data are qualitative, simply because if I reorder the names to be Frank, George, Harry, Bridget, Claire, and Melissa, instead of Melissa, Bridget, Claire, George, Frank, and Harry, nothing changes with regards to my interpretation of the data. There's no sensible ranking that I can make between these names that changes how I interpret the data. Okay? With quantitative data, the opposite is true. Okay, so if I take a quantitative data set, which is to say that I take a coin and I throw that coin 6 times into the air, and I count the number of times I measure a head. And then I do this over and over and over again. Okay? And then I plot the results. With my coin, I measure only one head 11 times. I measure 2 heads 9 times. I measure 3 heads 7 times, 4 heads 2 times. I don't measure any, there's never a circumstance where I see 5 heads, and I measure 6 heads once, all heads 6 times in a row once out of my N trials. This ordering makes sense. There is a measurable difference between the ordering or a sensible ordering that can be made of these numbers, right? I could order them like this, but arguably that would be silly, right? So there is a sensible way in which you can order these data, and therefore they are quantitative, right? It's the simplest way to think about it. This then leads to another distinction, which is between discrete and continuous data. So for quantitative data, if I have numbers, for example, then they can be both continuous or discrete. Qualitative data, somewhat by definition, are all discrete. You can't have a continuum of qualitative data, which we'll see in a second. The definition of these discreteness and continuous is somewhat important. Data are considered discrete if they can only take a finite number of values in any particular interval. Okay? So you can have a discrete data set that can take an infinite number of values. Okay? And a simple example of a discrete data set that can take an infinite number of values is the integers. Okay? Between any specified range, okay, say 0 and 10, there is a finite number of integers, but there is an infinite number of integers overall, right? And so the data are discrete, but can take a countably infinite number of possible values. Okay. So again, we've got this example of, like, in practice, examples of discrete data tend to be things which are counted. Okay, hence the integers example. So, for example, the number of successful heads that we measure on a coin, the number of electrons that are present in a detector, the number of galaxies in a survey, things like this. So these are examples of counting objects, and they tend to take discrete values. Continuous data aren't limited to a finite number of values in a finite range. Okay, so if I again take the interval 0 to 10, a continuous data set can have an infinite number of possible values within that finite range, and therefore the data are continuous. Okay, so an example of continuous data are just the real numbers, right? So not integers, but the number of real numbers is infinite between the range 0 to 10. Okay, the next fundamental thing that we want to talk about is what are called scales of data. And these are basically refer to the amount of information that is contained within a particular variable. And there's quite a bit of overlap conceptually between qualitative, quantitative, and scale. And that's essentially because the nominal scale is very closely linked to qualitative data. So the nominal scale is essentially any data that can't be ordered in a meaningful way. So these are all qualitative variables fall on the nominal scale. Okay. Ordinal data is data that contains, a data scale that can be ordered, but whose differences between different values can't be interpreted in a meaningful manner. So these are values that I can put in a rank order of sensible, this comes before that, comes before that, comes before that. But the differences between those values aren't meaningful. And a really simple example of the ordinal scale is like rankings of mood, right? There's a clear order in which these things should fall in order to make logical sense, right? Sad, somewhat sad, neutral, somewhat happy, very happy. But there is no meaningful interval between somewhat happy and very happy. Like, I can't meaningfully say the gap between somewhat happy and very happy is the same as the gap between somewhat sad and neutral. That's a meaningless statement. So these are ordinal data. The last of which are data which fall on what's called the continuous scale, not to be confused with continuous data, which can be ordered and the differences between their values have meaning. So these are numbers, right? Put simply. You can have other things. All right. So far, we've been looking at, yeah, that's a good question. So the ordering of, so we have a question which is the ordinal scale where I used names before could arguably be ordered, right? They could be ordered alphabetically, for example. But that ordering is different to the ordering that we have in an ordinal scale, right? The fact that I've ordered the names alphabetically, for example, doesn't change the fact that there is no reason a priori to put, the name Frank in front of the name Melissa, right? Whereas there is a justifiable reason, a quantitative reason to put very sad before sad, right? So you can rank things on a nominal scale for other reasons. Like you could order names, by alphabetic, as I said, alphabetically, but that doesn't influence the interpretation, right? Whereas if I was to reorder these ordinal values of neutral, somewhat happy, very happy, to put neutral at the front and then very sad at the end, but everything else the same, that would change the way in which I can interpret these data. It would make it more difficult to interpret these data. So it's a good question. It's a very good question. Cool. So we've been talking quite a bit about numbers of things, and we looked at coin tosses and we looked at names and numbers of names. These are all essentially measures of frequency. And this is the next thing we need to talk about. So when you're provided with a data set, the very first thing that most people do, and quite rightly, most people should do, is to ask the question, what form do these data take? Or rather say, what is the number of different values that these data take? Are they qualitative? Are they quantitative? How many entries do I have of a particular value, et cetera, et cetera? So these are all what we call frequency measures. We're going to talk about these for a bit. So let's start with a sample data set where we took 45 students and we asked them whether or not they prefer cats or dogs, right? That's our data set. I've created the data set in the background here. You can't see it. So you don't know the true fraction that prefer cats and the true fraction that prefer dogs. We're just given these 45 students the sample data set. And now, if we look at the data set, which I've just called OBS here for observations, our observations contain the student ID, which I've just given an integer number between 1 and 45, and the preference that they quoted, which is either dog or cat. Okay, so if we want to then say, okay, the first thing we want to say is I want to know the frequency of occurrences of cat and the frequency of occurrences of dog in my survey. And so we can do that again in R, just using this table function where I say I want to know the frequencies of, I want to create a table of the frequencies of the observations of preference. And what we get out is that 18 people said that they preferred cats and 27 people said that they preferred dogs. So this looks here like the dogs and cats have quite a distinction between the two of them. Okay, it looks like the dogs have slightly beaten the cats. This here is what we refer to as the absolute frequency, in the sense that it is the total absolute frequency of observations. However, frequently we don't really care, or we don't care most about the absolute frequency of observations. Instead, what we're using is a sample of observations to infer properties about the population. And so in that sense, it's frequently much more interesting to ask, what is the relative frequency of observations? So that is, what is the observations, the number of observations of each type divided by the total number of observations. So this is the relative frequency. And you can see that 40% of students seem to preference cats and 60% of students seem to preference dogs out of our survey of 45 people. This is just saying that you can do this. If your data are stored within a data frame, which they are in this, then you can use the n row to do this normalization. But if it's a vector, then you need to use the length thing in R. That's just a caveat of R. So here it looks like 60% of respondents have preferred cats to dogs. Is it significant? Is it not significant? Is it meaningful? What is the truth? What is the actual population parameters that have gone in? What is the true underlying distribution of preference of cats and dogs? These are all the sorts of questions that we're trying to answer in this course, or rather to learn how to answer in this course. Now, as a demonstration, the truth I can now tell you is that I fed these things, these preferences to be exactly identical. Okay, so this is randomly drawn from equal preference, and we've ended up with 40 to 60%, right? And so a lot of this course is going to be, how do we make statistical inference that is robust to sampling effects, like has generated this apparent difference between preference when in fact there is no difference in preference. So that's stuff that we're going to be looking at throughout the course of this thing, the course of this lecture series. One of the things that we often want to do is look not just at individual values, but rather graphical representations of those values. And we're going to see why that is in a second. So let's take a new data set here. You might recall that last week we looked at this New York City flights data set, which essentially contains all records of domestic flights that flew into New York, that flew out, was it into or out of? I think I've made a mistake there. I think that should say out of. Yes, I should have said out of. Right, that flew out of New York City in 2013. And so I've just read in the data set, which is this New York flights data set. And you can see that the data set, let me make this a bit bigger so it doesn't overlap. The data set contains, date information, year, month, day. It contains departure times, arrival times, the carrier, so which airline was flying it, the flight number, the origin, which is the airport in New York. So you have Newark, LaGuardia, and JFK, for those of you who have been to New York. And the destination of the flight is the location where it's obviously intended to fly to. And then there's sort of flight time details and things like that. Now, the reason why graphical representations of data are frequently useful to look at is essentially because when we look at absolute frequencies or even relative frequencies, with many different categories of data, it can very rapidly become inefficient to just look at numbers. So you can look at absolute frequencies, and that can definitely be interesting. So let's do, for example, the absolute frequency of the number of flights per month into New York. And what you can see is that on average, there's around 27, 28, 29,000 flights that fly into New York, that fly out of New York every year, every month, sorry. But if we don't want to look at absolute numbers, we instead want to know, for example, what is the fraction of flights according to each airline? Then we can look at the relative frequencies of each carrier. So we can do our table of the number of the carrier entries, of the carrier observations per of our data set. We can divide by the number of observations to get relative frequency. And that gives us these numbers here. And these are in scientific notation. They're a little bit hard to look at. So instead, we can reformat this just as a percentage of flights. So we can just do the multiplication of the fraction by 100 to get percentages, and then round it to 2 decimal places, because that's all we really care about. And we can then get this data set. So this is essentially the percentage of flights that flew out of New York as a function of the different carriers in 2013. And you can see that there are a couple of standouts. So these three here in particular, right? And this one here, where you have more than 15%. And just so that if you want to convert these code names into the actual airlines, that's what these are here. So you can see that the most common ones here, which are UA, B6 and EV, those are respectively United Airlines, as you might expect. B6 is JetBlue and EV is ExpressJet, so 2 budget airlines. So we can still digest this information. This is still not too many categories for us to be able to understand. But this can very quickly run out of steam. So for example, if we wanted to look at the absolute number of flights that flew out of each airport, you can see they're actually pretty evenly spread between the 3 airports. But if you wanted to do that for destination, then things obviously get a little bit out of hand, right? So it's quite hard to digest information from all of these different values, right? As humans, we're not very good at it. And so for this purpose, we usually look at graphical representations of data. Okay, so as a first example of a graphical representation, we're going to take that same histogram, that frequency of flights by carrier, and we're going to create a bar chart. So a bar chart's a very, very simple means of looking at the frequency histogram of the frequency of categorical data, of here qualitative data. And you can see that obviously there are these 4 standouts that we saw. These are the 4 airlines that had the most flights. And again, we can demonstrate that this is qualitative because if I reorder the x-axis here, nothing changes, right? And my ability to interpret these data don't change if I shuffle the x-axis. Okay, so these are qualitative data. The bar chart is really useful when you have these sorts of qualitative variables where you want to know the frequencies and relative frequencies of, but it becomes pretty unwieldy if you start to have larger numbers of categories. So for example, here we've taken this destinations that we had, and we said we wanted to look at the destinations in the number of flights to each destination. And you've seen that actually we can't interpret this really at all because the vast majority of the destinations have been hidden because the labels have overlapped. And so the way in which it's been plotted has been removed. We can make this a little bit easier to interpret if instead of saying I want to plot all destinations, you say I just want to plot the 15 most common destinations. And then all of a sudden the bar chart becomes useful again. Okay, so we can see that the most common destinations here are LAX, so Los Angeles, Atlanta, and ORD is Chicago O'Hare Airport. So these 3 are the most common destinations for flights out of New York. And so this is just an example of how you can use this graphical representation in order to understand the data set for qualitative data. If we don't have qualitative data, or rather we don't have data that sits on a nominal or ordinal scale, if instead we have continuous scale data, using the bar chart becomes kind of less useful. And the reason for that is because when we have continuous scale data, the X value means something, and the differences between the X value means something. So for example, if we go back to our coin tossing data set and we plot the bar chart of the outcomes of our coin tosses, then we see, okay, this is probably not a very good coin because it seems to be reproducing, fewer heads overall than you might expect from random chance. But more importantly, there's this gap here, or rather the lack of a gap here, where we have the difference between 4 heads thrown and 6 heads thrown has been smashed together. Because again, in this bar chart, there's no quantification of the meaningful difference between the X values. They are assumed to be meaningless. And so instead of showing this stuff as a bar chart, we then want to instead use something where we retain the information. We retain the information that's present in the x-axis, and that is the histogram. So essentially what we want to do is we want to count frequencies that fall within a certain interval. So again, if I go down here, I want to look at the number of observations that fall within the interval 0.7 to 1.25, 1.75 to 1.2 to 2.25, etc., etc., etc. And what you see when you make those observations is this: you have, 11 objects at unity, you have 9 at 2, 7 at 3, etc., etc. And now we have a meaningful gap. at 5, where we didn't make any observations. We've also got meaningful gaps between the values, right? And that's because the intervals that we requested included gaps where, by definition, there can't be any observations here because these are discrete values. These are discrete numbers that fall on the integers, right? And so these are 0 by definition, okay? These gaps in between. And that's interesting because it tells you something about the histogram. And that is that for equally spaced data, the area of the bar in the histogram is related or proportional to the relative frequency of the observations. And that's really important for how we as humans interpret these data. And we'll see more about that in a second. So here we've got this coin tossing data set where we have discrete data, but there is absolutely no reason that our histogram binning need be restricted to discrete data. So I can take 2 data sets or 2 sets of observations for one data set, which here I've constructed as being the number of mice in Disney films, which is a discrete value because it's an integer, versus the height of the mice in Disney films, which is continuous because it's a measurement of height, and constructed 2 histograms. And you can see that in the frequency space of per film, then there are an overdensity or an increase in the number of films that have 2 mice in them in Disney, but generally there's sort of 0 or more. Whereas if you look at the heights, there's a distinct population of mice that have heights that is less than 10 centimeters, which is sort of what I would say is arguably normal for a mouse. And then you have these 2 freakish outliers of Mickey and Minnie, who are both over 65 centimeters tall. So this is a good example of how you can generalize the histogram to both discrete and continuous data. But this lies an important caveat about the histogram. As I said, the bin width has meaning because the data scale, even if you have discrete, the data scale is continuous. And if you have equal bin sizes, so you don't have variable bin sizes, and you're plotting absolute or relative frequency. So let me put this another way. The area of the bins is proportional to the relative frequency unless you have both variable bin sizes, so I don't use equal binning in my x-axis, and I plot absolute frequency. If these 2 are satisfied, if you have variable bin sizes and you're plotting absolute frequency, the area of the bars in a histogram no longer is proportional to relative frequency. And we'll see why that is very, very dangerous in a few seconds. So what that means is that I can take this exact same data set. Notice there's a strong peak at 2 in the number of mice per Disney film, and there's a strong population that peaks around 7 centimeters in height in the height, but that these 2 Minnie and Mickeys are very, very much outliers. They're very unusual and they don't represent the normal distribution of data. If I take variable bin sizes and absolute frequency, I can construct 2 histograms that show almost the exact opposite visual trends as was shown in the above case. So I can show visually, it looks like there are many, many more observations of small numbers than large numbers in the number of mice. So it's a monotonically decreasing trend. And here it looks like you have a strong bimodality in the population and that there's lots and lots of things with Minnie and Mickey sized mice in them, right? And this is just due to the way in which the human eye interprets area in the histogram as being meaningful. And so in fact, if you try and do this in R and display data this way in R, you actually get a warning that says you shouldn't be doing this. You may well see the same behavior in Python. However, if you plot relative frequencies, or rather densities, on the x-axis, or you have equidistant bins, you can't create this problem. So here's the example of me showing non-equal bins, but now with fractional density or relative quantity on the y-axis. And all of a sudden we get back to the same sorts of display where you have a strong peak at 2, or, at around the normal, the number of mice in the mean of the population. So we have a strong peak around here, right? And less data on either side. And here again, we have a strong peak around 7. And, obviously Minnie and Mickey go back to being outliers in the distribution. And so this is an important caveat, an important thing for you to understand about how we interpret and how we read histograms. The next thing that you can look at is what's called the kernel density estimate. And that's essentially because the way in which we construct histograms artificially categorizes data. Okay, we make a decision where I want these bins to fall. So we have made an artificial choice about how I want to combine data together. One way around that artificial choice is what's called the kernel density estimate. And you can roughly think of a kernel density estimate in the simplest sense as being a sliding histogram, a histogram where the window that you are using to construct your histogram drags along the x-axis, and the value at every point is essentially the number of things that fall within that window. Mathematically, it's determined like this. And actually, if you construct the kernel density in a step-by-step fashion, which is what I'm showing with this animation here, then what you end up with is something that that sort of builds up over time. So I've got 400 observations of data that I'm fitting with a Gaussian kernel. So this kernel here, this K here, is the kernel that I use to make my kernel density. And what this kernel density is it's essentially just the summation of the kernel located at each point X of the data, right? Centered on each point X of the data with some width, what we call the bandwidth H, and then normalized so that it integrates to unity. So what you can see is I'm adding in data, and I basically take the kernel, which is this Gaussian you can see in the dotted line at the bottom, and I just add one of those onto the total every time. And that's what you can see is the difference between the black and the red. And so I'm building up, I'm doing this addition, I'm building up over time and building and building and building and building until I get to the end result, which is this red line here. This is my final kernel density estimate of my distribution of data, 400 data points, which I computed, which I just constructed, which the distribution of which is not, the true distribution of which is shown as this green line. So you can see the equivalent as a histogram as well, which is shown as the blue. So this is the artificial histogram binning. And then lastly, in the dashed line, you can see the kernel density estimate using a rectangular kernel, not using a Gaussian kernel. So that rectangular kernel has the same width as the bins of my histogram. So I've used the same width as my histogram binning for the rectangular kernel. But essentially what's happening is it's dragging that rectangular kernel continuously across the x-axis and giving me the number of observations that fall within that rectangular kernel instantaneously at every element. And so there is no discretization of the data in the kernel density estimate. And that's the main utility of the kernel density estimate. Another thing that we can do to quantify the different sort of distribution of data that we have in a particular variable is we can look at what's called the empirical cumulative distribution function, the ECDF. So let's start with some discrete data. We're starting with our coin toss data set again. So here we have a coin that we just found on the ground. We don't know whether it's a fair coin or not. We throw it 6 times and we count the number of heads that we get in a row. And then we do that again and again and again and again. And we see that the coin gives 1 head most frequently, and then 2, and then 3, and then 4, and then 6. Now, if instead of looking this in terms of the frequency, just the frequency of each value, I instead look at the cumulative version of this frequency, I get this. So I basically take the cumulative sum of this distribution along the x-axis. And so when I hit 1, all of a sudden I go from no observations to 11. If I then step into this gap, obviously I don't add anything. So the value stays the same. I then add another 9, and then I hit the gap, and then I add another 7, etc., until I get to 6, where I add the last data point here. So this is the cumulative distribution of that frequency histogram. And the ECDF is essentially something quite analogous to this step function that we've just created here. So it's the same sort of thing, except it's normalized such that it shows the relative fraction of data. So the relative frequency of data, cumulative frequency of data up to that point X, up till the point on the X-axis X. So again, we calculate the ECDF of this coin toss data set. We have 40% of the data are observed at a value of 1, or rather are observed at a value less than 2. If we then go to a value between 2 and 3, we have 65%, 70%, etc. And we go da, 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 da. So this is the empirical cumulative distribution function. Similar to like we saw with the histogram, we can generalize the empirical cumulative distribution function to continuous data, because it basically just does exactly the same computation, but for the continuous data set that we have. And so you can take, for example, a continuous distribution of data, which I've shown here using the kernel density estimate of a bunch of randomly distributed data. So here what I've done is I've used the random normal function in R to generate 10,000 random normally distributed data points. And then I've used magplot to plot the kernel density estimate, which is used just using this thing called density. And then I've labeled my axes, as you always should. And what you can see is that you have the KDE here, and for some reason the plot hasn't shown up. So what I'm going to do is I'm going to go over to my little console here, and I'm going to do this live. rnorm 40. Da, da, da. So I've just created the same data set. I've now plotted the density of that data set here. And now what I'm going to do is I'm going to plot the ECDF of that data set. And this is what the ECDF of that data set looks like. Okay, so again, it looks more continuous now, and it basically describes the fraction of data that fall up to the value on the x-axis. So here you can see the peak of this distribution is around 0. And indeed, if you go to 0, you have 50% odd of the data set falls less than 0. Okay. One important thing to note about the ECDF is that while it looks like a continuous function for the continuous data set that we just constructed, that's not necessarily the case. Okay, so if I was to plot the ECDF again, but now to look specifically at a very, very small range in the x-axis, and this hasn't plotted again because I've made a mistake with my R markdown. If I look now, if I zoom right in on this function to look just around the very middle, I can actually see that no, this isn't a continuous function. It is still a step function, right? There are still plateaus here. And what that means is that because this is a step function, I can't invert that function, because if I was to invert the function, all of a sudden at a single value x, I have a range of values of y, and that function is undefined, formally undefined. And so instead, we have a different function that basically interpolates between data sets, between individual data, and that function can be inverted. And the inverse of the ECDF, the inverse of the cumulative distribution function, is what's called the quantile function. And this is a really important function we're probably going to see a lot of in this course. And so what the quantile tells you is, at a given fraction of my data set, what is the value? So it's just, as I said, it's conceptually the inverse of the ECDF, but in practice, we use an interpolation between the data to get the quantile function, so that because that's invertible. So in R, you do this using the quantile function. In Python, you use, again, just numpy quantile, similar sort of thing. And what I've plotted here is the quantiles of my same random normal data X. And you can see that at 0, the quantile is, something quite negative, and at 50%, my quantile is around 0, and at 100%, it's something quite positive. So again, it's as if we've just inverted the ECDF, but practically we had to do something slightly different. In R, there are a total of 9 different ways that you can compute this function. Some would say that is unnecessary. Statisticians would say that is appropriate. The number of different, or the different algorithms that you can use to compute the quantiles are, for your purposes, largely irrelevant. For our purposes, our quantiles are always going to be computed using the default function in R, which basically just uses a linear interpolation between continuous data points. What that means in practice, again, you don't really need to know, but just if you're interested as to why R has 9 different algorithms, it's just because of different ways of creating this function so that it's invertible. Okay, this brings us to the last section that we're going to go through in this lecture, which is measures of central tendency and dispersion. So while we have looked so far at frequency measures, so we've been looking at the numbers and the relative and the absolute frequencies of data, it's often desirable to reduce a data set to a single value, or to a set of values, a set of what we would call summary statistics. And those summary statistics generally, at their simplest, can take the form of a measure of the central tendency, which is the most common value of a particular data set, and the dispersion, the spread of the data around a particular value. And so you'll have very likely heard a number of these estimates of central tendency: mean, median, and mode, things that we cover all the way through high school, but I mean, it's always good to have a refresher. And dispersion of the data, things that you might not have heard of. So things like standard deviation, the root mean square, and the MAD, which we'll go through now. So when it comes to point estimation, there are 3 main ones that we're going to discuss. The first of which we should all be very familiar with, which is called the arithmetic mean. The arithmetic mean is just the common average that we're all familiar with. So it's the sum of all of the values divided by the length of the vector. And the arithmetic mean is generally given the symbol x bar. And I think we should all be fairly familiar with this. The next item is the median, which we come across far less frequently in our day-to-day lives. The median is the point that divides the data set into 2 equal parts, which for an uneven data set is quite easy, and for an evenly numbered data set is quite complicated. And I've just realized I've got this ordering incorrect. There's a lot of mistakes in this lecture. I should have read this better. My apologies. I will correct these prior to publishing. So the median is formally defined for an odd data set as just being the middle value, the middle one of the data set. So if I have 11, if I have a vector of length 11, and I rank order the vector so that it is increasing in value, then the median is the entry that has 5 values on one side and 5 values on the other side. For a evenly numbered data set, so for a set where the length n is an even integer, is what this is saying here, the value is the linear or the arithmetic mean of the 2 middlemost values. So if we had a vector which was of length 10, the median is the mean of the 5th and 6th values. Arithmetic mean of the 5th and 6th values. However, those of you who remember what we just spoke about with the quantile function will realize that that's the same prescription that we use to define the quantile, which means that the 50th quantile in our standard interpretation or standard implementation of the quantile function is identical to the median. And this is going to be something that's quite relevant later on when we talk about dispersion. The last measure of central tendency that we're going to discuss is the mode. And so here we have, for example, our data set again, and we take the KDE, the kernel density estimate of our normally distributed data. We then plot the kernel density estimate, and then the mode we define as being the most common value, or the most the point on the kernel density estimate with the greatest density. Okay, which we've defined here as being the point in X, which has the Y value is equal to the maximum of the Y values. Okay, and that's the dashed red line here. So this is, again, this is just the measure of the mode. And so the mode is, again, another useful tool of central tendency that's going to become quite important a bit later next week when we talk about the differences between all of these different point estimates. The second thing that we're going to talk about is slightly more complex, which is about measures of dispersion. And so dispersion is essentially a measure of the amount of spread that a data has around a particular point. Okay, and there's a few very, very important reasons that the dispersion is important. The first of which is that you can have two vastly different distributions that have the same central tendency. You can have two vastly different data sets that have the same mean value, right? That should be clear. And therefore, summarizing data using a single point estimate is frequently insufficient. The second is that when you're quantifying the range of a variable, a point estimate isn't useful, right? Again, that should be fairly clear. If I want to know the range that a potential variable can take, then I can't summarize that using just a mean or a median. Even if we do just want a point estimate, the dispersion is still fundamentally, crucially important. And that's because the measure of accuracy of a point estimate is usually intimately linked to the dispersion of the data set. That is to say that my accuracy with which I can determine my mean is fundamentally linked to how highly dispersed my data is. My mean of a particular Gaussian is very, very accurately determined for a low dispersion measurement with N data compared to the same mean computed with a very broad dispersion. Okay, and we'll see a bit more about that a bit later. And so, put simply, the dispersion is very important, and so we shouldn't forget it. Let's construct a simple measure of dispersion. We're going to call it the deviation, okay? And the deviation, we're going to simply define as the deviation, D, around a particular point A, is defined as the sum of the differences between our data and that point, A, divided by N. So it's the arithmetic mean of all differences between the data and some point A, which we define arbitrarily. So let's write up this little dispersion code. Let's take a set of observations. Here I'm generating a bunch of exponential data. Again, we'll see more about this distribution later on in the course. But let's just say I've got some exponential data, 1,000 observations, and I define my dispersion function as the dispersion of X given A. The dispersion of X given A is as I said, is the sum of the differences between X and A divided by the number of elements that we have. Okay, and then I compute the histogram of my observations, which is shown here. Let me make this a bit bigger. So I now compute the histogram of my observations, which I've shown here, and I compute the dispersion of those observations, which I show by the red line. And that looks pretty good. All right, so our dispersion estimate is a pretty good estimate of the actual dispersion in the data. In fact, if we go back up here, we can see that I created this data set with an intrinsic dispersion of 1, which is what's given by this rate function. And the value that I get is pretty close to 1. So it looks good. Let's now try again with a different data set. Let's try with a Gaussian data set rather than an exponential. So I'm going to take my random Gaussian data, which has 1,000 entries. I'm going to compute the histogram of my Gaussian data, and then I'm going to compute the dispersion of that data again. And now, all of a sudden, our dispersion measurement is centered on 0. And that's clearly not good. Okay, because now our dispersion measure seems to be telling us that there is no dispersion in this data set when quite clearly there is quite a bit of dispersion in our data set. So something's clearly broken down here. And the thing that's broken down is that in our measure of dispersion, we used the sum of the differences between the mean, between the data and our point of interest. And our point of interest for these observations or these dispersion measurements was 0. Okay, and so what's happened is with our Gaussian example, we've summed together all of the positive differences, and then we've added all of the negative differences, and obviously we've got cancellation, and we've ended up with something that is 0. So instead of doing this, if instead what we want to say is, okay, this is clearly no longer a good measure of dispersion because it doesn't allow for data that is both positively and negatively distributed around our point of interest, which is 0 in this case. And so we define a new measure of dispersion, which we call the absolute deviation, which is the same as the formula we just had, except we take the absolute value of x, x minus a, xi minus a. So we compute, we redefine our function here as being now the dispersion is the sum of the absolute values of x minus a, and we replay our game with our Gaussian function, and hey, now we end up with a measure. We've got 2 lines here now because we took the absolute value, which gives us 2 solutions at plus and minus the dispersion measure that we have. And our dispersion measure is now plus minus 1, which is good because that's a pretty good estimate of the dispersion of the data. Now, it's worth noting that our dispersion measure here still carries with it our choice of A. So here we defined A to be 0, just because. We can choose A to be something else, right? We can choose A to be something meaningful. Like, why don't we choose A to be one of our point estimates? Let's choose A instead to be, for example, the arithmetic mean of the data set that we're analyzing. And that gives us what we call the absolute mean deviation, which is, D of the mean, the arithmetic mean, and that's what's shown here. Or we could use A as the median, right? And that gives us what's called the absolute median deviation. Again, something here. And these are both measures of dispersion that one might want to use. It's worth noting, however, that this choice to take the absolute value of our deviations isn't the only one that will give us values that behave sensibly with negative and positive deviations. Okay, one other method might be to take the square of the deviations. And if we take the square of the deviations, again, allowing for an arbitrary central point, A, then we get what's called the mean square error, which I've scrolled down to. So this here is called the MSE, or the mean square error, and it's defined as S squared of A is just the sum of the square, the arithmetic mean of the squared deviations from the point of interest. The MSE is a particularly useful function, is a particularly useful thing, and holds a somewhat special place in statistics, as we'll see a bit later in the course, because you can use the mean square error for determining whether an estimate of a particular parameter is biased or unbiased. That, again, might mean not a great deal to you at the moment, but it will be something that we talk about a bit later on in the course, so it's nice to hear as a flag in the beginning. So a very important thing to end this lecture with today. So this is going to be the last thing that we talk about. If we set A to be the arithmetic mean of the property of the distribution, the MSE becomes what's called the variance. Variance is a very important value in statistics. So the variance of a distribution is defined as the mean square error using the arithmetic mean of the distribution as a reference point, and is defined as this. Equally important to the variance is this positive square root of the variance, which is known as the sample standard deviation. Okay, and this is a parameter that you've probably heard a lot of, the standard deviation. The sample variance and the standard deviation are very, very fundamental to a lot of statistics. And we're going to be hearing these two words quite a lot. We're going to be talking about how you minimize the uncertainty on these things during our next lecture. One important thing to note, though, is that this formulation of the variance and the standard deviation is the sample variance and the sample standard deviation. One of the things that we're going to find, though, is that, as I said at the beginning, we're often frequently interested not in talking about the properties of the sample. We're interested in talking about what the sample tells us about the properties of the population. And it turns out, for reasons that we're not going to look at right now, but we'll see later, that the sample standard deviation, or the sample variance, isn't an unbiased estimator of the population standard deviation and the population variance. But it's quite easy to show that the unbiased estimator of the standard deviation of the population is, or the variance of the population, is quite similar to the sample variance. It's just instead of divided by n, it's divided by n minus 1. And this is an unbiased estimate of the population variance given a sample of observations. That difference, that n and n minus 1 difference, both of these things are frequently called standard deviation in the literature and in textbooks and things like that. And so you may see both, right? The difference is that this is a measure of the variance of the sample, and this is a measure of an unbiased estimate of the variance of the population given the sample. Okay, so again, if that might not be clear, but hopefully we'll make that a bit clearer later on. Okay, the last measure of dispersion that we're going to talk about is what's called the median absolute deviation from median. So you'll remember that we looked at the absolute median deviation we defined here, and that's the arithmetic mean of the deviations around the median. But instead of doing that, we can look at something in terms of just purely median statistics, and we can compute the median deviation from the median, and that's called the MAD, the median absolute deviation from median. But the MAD is really, really useful. The MAD is really useful because it's not sensitive to outlying data. Because the variance and because the standard deviation contains the arithmetic mean in it, if you have a very, very far outlying data point, think, Mickey and Minnie in our mouse heights diagram, those two outlying data points can drive the arithmetic mean. This is something that we're going to see a lot of tomorrow. Next week, not tomorrow. And that means that the standard deviation estimates for real data sets can become biased. And so what we do instead is we can use the median absolute deviation from median to estimate the standard deviation in the presence of outliers. But just this straight thing doesn't actually give you the same information, the same value as a standard deviation, right? So if I create this function in R, MAD dispersion is equal to the median absolute deviation from the median, and I just look at the standard deviation of my random normal data compared to the MAD dispersion, these things are very different. But it turns out that the difference between these things is actually just a multiplicative value for normal data, for Gaussian data. And that multiplicative value is this, 1.4826. You don't need to know where it comes from for now. You just need to know that it exists. And that means that we can define the normalized MAD, normalized meaning that for normal data, it returns the same thing as the standard deviation. And that's in fact what is defined by default in the implementation within R and within Python and with everything. Every time you see MAD, what they really mean is normalized MAD, basically speaking. And so if I use the standard deviation and the MAD for my data, then I end up with these two things here. Okay, that's basically what that was all we wanted to talk about with today's lecture. There's going to be a lot of discussion next week about all of these different things and how they fold into and how we can use them to compare the behavior that they have on different data sets and on different statistics, different distributions of data. And hopefully that's all been fairly clear. I know that was somewhat of a shopping list of things, so my apologies for that. But hopefully now, when we get into next week's course, what we're going to be talking about is basically how these point and dispersion statistics differ, and where they're useful and da 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 da. So if I go back to our introduction here, you can see that we've got the values. This is what we're going to be talking about next week. So we're going to be looking at the different comparisons that we have between data sets. So how we're going to be how these different point estimates differ in given a whole bunch of different data sets and different properties of data. And we're going to look at this important two things called correlation and covariance. And then we're going to end by basically, I'm going to throw a couple of random data sets at you. And together we're going to go through and do some data mining and see what we can learn about these two data sets, given that you guys won't know what's in them. So that'll be a little bit more interactive, I hope. Right. So we've got a question here, which is just asking about the lectures. So I'm leaning towards not uploading the recordings of the lectures, but rather to have the questions that are asked during the lecture provided with answers along with the lecture notes, which will be provided also in the Moodle. So the lecture notes, which are these slides that I'm going through, will be provided along with the R Markdown version, which means that you'll be able to access all of the code and everything. And if people would like a brief video of how to use R Markdown and stuff, then I'm happy to provide that as well, in addition to what's in the lecture notes. But for the recordings, I'm not planning on releasing the recordings. The main reason for that is because I would like people to attend the lectures and engage with the question and answer as much as possible. And I feel like if I provide the recordings, then that's less likely to happen. Of course, if I'm still going to record these lectures for my own posterity, and if, for example, there's a reason why you can't attend a lecture, then we can make an arrangement where I can give you the recording for a short period of time or something like that. But as a general rule, I'm not going to release the recording. No. Okay. How do we calculate the error for the median of a sample? Yeah, that's a really good question. So one of the things that we're going to look at is basically the measures of dispersion and how they tie in with basically our uncertainties in each point estimate. So one of the things that when we started talking about the point estimates, if I go here, or rather, where was it? Dispersion here. One of the motivations that I gave for knowing the dispersion is being able to estimate an uncertainty on a parameter, on a point estimate. And as you say, that's crucially important for something like a median, which naively doesn't have also for the arithmetic mean, naively doesn't have a simple uncertainty estimate. It turns out the best way to estimate uncertainties on these parameters is using dispersion or using a measure of the dispersion, and that's something that we're going to talk about next week. Yeah. Great. If there are any other questions, then feel free to add them to the Slido as last week. The Slido is going to be open for the remainder of the week. Should people want to put in slides after the questions after the lecture, if you come up with something. Also happy to take questions now, just if people want to pipe up and talk. Otherwise, that's all that I had for today, and I look forward to seeing you all next week for the for the next section, which again is going to be discussing the differences between point and dispersion statistics and correlation covariance and some data mining. But that's all for me for this week.
Thank
Great.
you. See ya.
Nice. So if there's no questions, then feel free to sign off now.
Okay, bye.